Okay, all right. So today's problem is going to be, uh, all right, so today's problem is combination sum 2. Uh, Given it is a medium, given a collection of candidates, and a target number candidate, we are going to find all unique combinations in candidates in which the candidate numbers sum to target. Each number in candidates may only be used once in the combination, and the solution set must not contain duplicate combinations. So if you've ever done combination sum 1, the only difference, I believe, between the two of these is the allowing of duplicate combinations. I actually could be wrong, but I actually don't think there's even duplicate numbers in combination sum 1. So I actually, oh, well, all right, so combination sum 2. All right, so the problem we're going to be doing today is combination sum 2. It's a medium. Description is given a collection of candidate numbers candidates and a target number target, we're going to look for all combinations in candidates where the candidate numbers sum to target. Each number in candidates may only be used once in the combination. And note, the solution set must not contain duplicate combinations. So I believe the only difference between this and combination sum 1 is that we're not supposed to include duplicate combinations. I believe in combination sum 1, which you should probably do before this one. I don't think there's even duplicate numbers inside. I could be wrong though. So let's look at the examples. So if we look at these examples, we can see, right, we look for 116, so we have 1, 1, and 6 adds up to 8, 1, 2, 5 adds to 8, 1, 7 adds to 8, 2, 6 adds to 8. So these are all of the combinations within that add it to it, and it doesn't include combinations, right? So if we have, or it doesn't include duplicates, right? So if we have 1 and 7, we're not going to include 7 and 1. So I actually don't love these examples. I think they're really large, and it's really hard to see and visualize in your brain how you're going to look at this problem as a whole when you're looking at this big of a sample size, because this is a huge. It's what, 8, 1, 2, 3, 4, 5, 6, 7 numbers. 7 numbers, but that's big when we're looking for every combination, and that should actually give you a hint as to you should not be scared if you're coming to a large, like a really bad time complexity. Another hint of that is that candidate's length is going to be less than or equal to 50. So we're dealing with really small sample sizes here, which means that our time complexity is going to be bad. We need to check basically every combination in the worst case. So I like to look at it with an example like this, right? So let's say we have 1, 2, 1, 1, and our target is 2. So we're going to start at this first number. We're going to see that we're going to start with 1, right? We're going to start with 1. 1 plus 1 is equal to 2, so we have 1, 1. We have another one, we have 2. 2 just by itself is actually an answer as well, just because that's a number. That's a number that adds up to be our target sum. 2 plus nothing is our target sum. And we also have these, right? So we have 1 and we have 1. We can include that, but that wouldn't be correct because we already have it here. So we actually just have this as our answer. This is the only things in this combination that add up to 2 with no duplicates. So how do we get there algorithmically, right? So I like to think of these kinds of questions as, I like to draw out a decision tree, right? So if I have my initial, I either I have the decision to include 1 or to not include 1 for every single value. So what does that mean? So I have the decision here to include 1, or I have the decision to not include 1. And when I have the decision to include 1, I now have the decision to include the next number, 1, 2. And now I have the decision to not include the next number and go to the next, which would be the next, which is 1, 1. And then a decision not to include that, and then the decision to include or not include from there, which this would actually be our final answer. 1. This would be the, not final answer, sorry, this would be the end of the decision tree, expanded for all of these guys here. So we could go through and check all of the different values, but there's 2 problems with that. One, sorry, check all the values for summations of 2, or of our target. We could do that, but there's 2 problems. One, it's really inefficient, right? There's no reason to continue, right? So if I have this guy here, our sum is equal to 3, and our whole array is positive integers. So if we continue to add numbers to that, we know that our target is only going to decrease. So our target is now, so when we went to this value here, our target is now equal to 1 because we subtracted the value. And then when we went to this guy here, our target is now equal to -1. So if we continue to traverse down this guy, there's no point because we know that there's nothing's going to happen from that. So that's our first issue, is that it's really slow and there's no need to continue searching. Our second issue shows up right here. So we found 1, 1, right? But we also found it again. How do we know to include? Do we check the entire list for repeat values? No, that would be really inefficient. We're actually just going to stop. So, or sorry, we're not going to stop. We're actually just going to have to find a way in order to skip duplicates when we've not included a value, right? So what do you notice, right? So we go down this and we find this 1, 1. And now, when we find this 1, 1, if we know we go down this path, there's no reason to keep checking values of 1. Sorry, 1 is really confusing. There's no reason to keep checking values of candidates 0, right? Because we've already checked given that value. There's no reason to continue traversing down this list because we've already checked all the combinations with that value because this value is 1. So if we continue checking now, we know we're going to probably find duplicates. So what's the solution, right? How do we find a way to skip values only when we're going down a path which we haven't included the value of? Solution is actually going to be to sort first. We don't need to be scared of sorting here because we know that our time complexity is going to be dominated by this recursive backtracking. So because sorting is only n log n and recursive backtracking is going to be much slower. We can get to the actual time complexity later, but we know we can sort, right? So we have 1, 1, 1, 2. So how does this change our decision tree? So we start here, and then we go here. We go 1, and then we go here. And then we continue down our DFS. We are doing a depth first search of our decision tree. We continue down our DFS, and we go 1, 1. Sum is equal to 2, so we know we can return. What happens when we go down this path, right? It's 1, but we want to know what next value we should include. We know we can't include this next one because it won't have a duplicate. So we know that if we've not included, we now need to skip all duplicates of this value here. How do we do that? We just skip. We just write a while loop and we skip through, right? So we skip to this value and then to this value and to the next value. So now we have 1, 2. But this sum is equal to 3. So we can actually just return. And now we go to this not include value, so now we have 1. This is the end of our traversal. We return, and now we have 2. And we have 2 on this side, right? Because, or sorry, not 2 here. We can include a value of 2. This sum is equal to 2, so we know we can return. And if we don't include, there's no more to traverse because that is the end of our list. Okay, now for the actual implementation, right? So we want to start out with our sorting, right? So we want to take candidates and sort. Next, we want to define our current array and our answer array. Oops. And now we want to define our DFS, right? So we write define DFS, and we want to keep track of two values, right? We want to keep track of the index that we're currently on, and we want to keep track of the target value that we're trying to reach, or the target value that we've, the target value we're trying to reach given the point that we're at in our DFS. So that's going to be equal to I and target. So now our next step is to define our base cases, right? Because we're doing a recursive depth first search. So we define our base cases. We say first case, right? So first case is going to be if I is less than 0. So if target is less than 0, then we know that we've gone too far, and then we can just return. Next is if target is equal to 0, then we know that we found a solution. So we actually take our current array, we take our answer, and we append our current array. And then we return, because there's no reason to keep checking if we've already found a solution. Also, we know that we don't need to be concerned about finding like zeros, like 5 plus 0, because we have our candidate values are greater than 1, or greater than or equal to 1. So now we just write our while loop, right? So we have to write a while loop that continues for each of the values in candidates. So while I is less than candidates, length of candidates, we are going to first add our current value to candidate, or to our current. So current dot append candidates I. Then we are going to run a DFS with the next index value, and with our target now subtracting our current candidate's value, right? Because we know that we've added it. And now we pop this back value from the end, because we are going to backtrack and check all of the rest of the values, given that we didn't include that last value, right? But what do we know about checking the side of the tree that doesn't include that value? We know that we need to skip duplicates at this point, right? So that's actually not very hard. We just write a while loop. So we say while candidates I plus 1 is equal to candidates I, so that while the position that we're currently at is equal to the next position, we continue to increment I until we get to a point where it's not the same value. And we also don't want to check outside of range, so while I is less than length of candidates minus 1. So while I is less than length of candidates minus 1, we know, I'm messing things up here. So while I is less than length of candidates minus 1, and the candidates I plus 1 is equal to the candidates of our current position, we increment I, and then we increment I at the end. And now we can just run our DFS, right? So we have our DFS. We start at the position 0. We start with our target equal to our initial target. And now when we run this, our answer will populate, and then we can just return our new answer. So let's submit it. I accidentally messed up, actually. So we actually have to keep this while loop inside of this other while loop. I accidentally messed that up. So there you have it. Passes, and it's pretty efficient.